Hello. Today we're going to be deriving the heat equation using two different methods. Very similar approaches, but slightly different. One is by looking at a thin slice and then taking a limit, and the other is using conservation of conservation of thermal energy and integrals. And you'll see they're pretty similar, but also slightly different. So first, we need to define some terms. We have E, which is thermal energy density, right? This is energy per unit volume, and I should say thermal energy per unit volume. Now, if you multiply this by volume, you'll get then the thermal energy. And what we can say is that, so for example, let's say we have a shape like a rod, and we'll be looking specifically at heat equation for one dimension. I should also mention that. And so let's say we have a one-dimensional rod with a cross-sectional area A and a length change in X, right? Which is just like a thin slice. Then we can say that the thermal energy within that slice is E times A times change in X. Cool. Now, the rate of change, or here, wait. The rate of change of thermal energy, thermal energy over time is equal to two things. One is the thermal energy flow across the cross section. So you'll see in the diagram there's two cross sections, and thermal energy could be flowing in and out through these two different cross sections within this volume that we're looking at. So that could be one cause for the change of thermal energy. The other one is internal. Let's say that there's like a flame to it, so thermal energy is being added to it, or internally there's like a chemical reaction. So then thermal, there could be a source or a sink of thermal energy within. So I'll label that a source or sink of thermal energy per uh per over time. And specifically, we're looking at the rate of change of that source or sink of the thermal energy over time. Now, what that means is that we can say that the partial derivative with respect to E over T times the cross section times change in X, because if thermal energy is E times A times change in X, and A and change in X are constant over X and T, then the rate of change of thermal energy over time is just partial E over partial T multiplied by A times change in X. That should equal what's called the flux from X comma T subtracted from the flux of X plus change in X comma T times change in X, or sorry, times A. So for flux is just the amount of thermal energy coming out of this the amount of thermal energy coming out of this cross section per unit time. So we can say its units are energy over area times time. And we have to do this for both sides and subtract them to get the difference, so that we can figure out the changes. And similarly, the rate of change of source or sink of thermal energy over time, we'll just call it a variable Q, which is Q, we'll say, is the uh, thermal energy density, energy over volume, thermal energy density over time, so that the rate of change of the source of sink of thermal energy over time is Q times A times change in X. Cool. So now we have this equation that describes a physical property that kind of makes sense based on intuition into some math, and we can do some manipulation to it by dividing both sides of the equation by A times change in X. And we get change in E over change in T is equal to the flux at X, comma T minus flux at X plus change in X, comma T over change in X, because the A's cancel, and so you're just left with over divided by X plus Q, because the A and the change in X cancel. And if we imagine this slice to be an infinitesimal slice, that is, that the limit as change in X approaches 0, you'll see this is the definition of it. This is the limit definition of a derivative. And so we can rewrite this as partial E over partial T is equal to partial phi over partial, or I'm sorry, partial phi over partial X plus Q. And so this is called the conservation of thermal energy equation. It just says that the rate at which the thermal energy change should be equal to the rate of change of thermal energy coming in and out, which is the flux, plus any source or sink of thermal energy from within. Okay. And now the next step here in our derivation is that the variables E and phi are kind of abstract. So we want to be able to relate them to more physical properties that make sense. So first, E. If you've taken chemistry before, you know that thermal energy, you know about specific heat capacity and how we can use that to convert from thermal energy to temperature. Simply put, thermal energy is equal to C times rho times C times rho times U of X comma T, where C is the specific heat capacity, which kind of just says that it's a property of every material that says for a given volume how much energy you need to increase its temperature. It's in units of joules or energy, a unit energy per volume time. And similarly for rho, rho is just mass density. So its units are just mass over volume. And wait, oh, sorry. This is in units, not a volume times time. I made a mistake here. It's in energy per mass. So for a given mass of a substance, how much, wait, sorry, I messed this up. Let me try this again. Uh, it's an energy per mass times temperature in degrees Celsius. Sorry. Right? So it says that for a given substance, because every single material has a different heat capacity, but it says for a given material, this is the amount of energy it takes to increase its temperature, this much mass of a material by this temperature, how much energy it takes to do that. Uh, and so rho is defined mass density, so mass over volume, and then temperature, uh, here, U of x comma t is just equal to the temperature, uh, which is a temperature which is dependent on the position as well as time, right? And so you see how all the units work out so that we get thermal energy is energy over volume because the mass cancels and the temperature cancels, leaving energy over volume. And so we can rewrite this now if we assume specific heat and mass density to be constant, which we will, then we can rewrite this as C times rho times partial U over partial T equals partial phi over partial x plus q. Now, for partial phi partial x, we're going to do another derivation. So for this part, we're going to need to introduce something called Fourier's law, which is it's just like a law that comes from intuition. You can comes from intuition. It says that the flux is equal to minus k naught partial u over partial x. Now this equation, it simply came from observation. Fourier noticing that, hey, if you have like a temperature gradient, like if you have something hot here and something cold over here, then, right, hot to cold, the temperature of this will increase. It'll go opposite to what its value is. And similarly, this will decrease. It'll go opposite to what its value is. So he noticed a proportion where the flux, or the change in temperature per unit volume, is proportional to the change in temperature over some distance. So over this distance, because the change in temperature goes from hot to cold, you see the hot reducing, reducing and the cold increasing, right? And I should put a minus here, I forgot. And so then you can convert this to an equation by just putting a constant, and this constant K naught is just thermal conductivity, which is again just a property of a material that you can figure out empirically. But we can now put this into our equation, and we can say that, okay, partial phi over partial x, we can rewrite now, and we can say it's K naught partial u over partial x, or sorry, minus K naught times partial u over partial x plus q. Now, if we assume that C, rho, and K naught, which are these properties of materials, if they're constant, that is to say, independent of both time and position across the material, and we also assume that there are no sources or sinks within the material, that is Q equals 0. If we make these two assumptions, we can now rewrite this equation. Or sorry. Wait 1 second. I made a mistake. My bad. So it's the part it's the partial derivative with respect to x of minus k naught times partial u of x, because this is the flux. And so anyways, back to this, if we make these assumptions, we can now rewrite this as c times rho times partial u over partial t is equal to minus k naught times partial squared u over partial x squared. And then we can take all these constants and put them into one constant. So now we get partial u over partial t is equal to minus k, where k is k naught over Cp times the second derivative of the temperature over distance, over position. And this is the heat equation.